Hi, everyone. My name is David Amaro. I'm a research scientist at Quantinuum, working in London. And today I would like to talk to you about the recent work that we have done on protecting expressive circuits with a quantum error detection code. So I hope that at this point of the conference, we are convinced that quantum computers have the problem or the challenge of errors. They are everywhere in our quantum hardware, and we need to find a way to correct them. We believe this cannot be achieved only at the hardware level, so we need to prepare to use more clever techniques at the software level, design our quantum circuits in a clever way to reduce the errors. And the techniques that provide us this protection on the design of the circuits are called quantum error correction or fault-tolerant quantum error correction. So the basic idea is that we're going to design our quantum circuits with more qubits and more gates. So that means we're going to add an overhead of quantum resources that will give us the ability to correct the errors. And fault tolerance is the key property that will give us that level of protection. So I want to start by showing a really impressive experiment performed on a trap-ion computer at Innsbruck. And the authors demonstrated the implementation of one important primitive for fault-tolerant quantum error correction. It's the implementation of a magic gate, a non-Clifford gate. So this is something that any quantum computing platform can do without fault tolerance. You can initialize one single qubit and implement one single qubit gate. But this naive implementation doesn't have any level of protection. So the fault-tolerant implementation will have the key design to protect the implementation. And it just becomes a bit more complicated, as I want to highlight here. This is the fault-tolerant implementation. This is the physical circuit. And from here, it has several steps. I want to highlight the first three on the top row. So as you can see, I will not go into the detail, but you can see that we have to add more qubits. So instead of 1, we have 15, and we have to add more gates. Instead of one single qubit rotation, we need to add many CNOT gates and measurements and so on. So this circuit is extremely difficult to implement, but it has a really clever design that has this property of fault tolerance. It means essentially that no matter what single component in this circuit fails, the circuit can be corrected. So obviously, it has a limitation on existing devices. We cannot implement circuits as complicated as this, and especially when we want to implement more advanced algorithms like QAOA, VQE, quantum Fourier transform, Shor's algorithm, very expressive circuits. The resources that we need from fault-tolerant quantum error correction are too much for existing devices. So this is the picture that I want to show you. At the moment, we live in the NISQ land, so the land of errors, where we try to do our computations, but we sometimes fail, or at least it's really hard to obtain very meaningful results because there are errors everywhere. And we want to get to the mighty land of fault-tolerant quantum computation, where everything is almost noiseless. And over the next years, we will be moving from the NISQ land to the fault-tolerant land by adding slowly some quantum error correction primitives, error mitigation, and improving the hardware. And it's possible that we find quantum advantage along the way. If we are able to reduce the noise to the desired level, that can be enough for certain applications. And It's not moving? Okay, now. So with this idea of using partial fault-tolerant error correction, we have developed or used the iceberg code specifically for Quantinuum devices. The idea is that this iceberg code is known as a maximum separable quantum error correcting code, maximum distance code, and is defined in this way. We have, there's a typo there, it should be k plus 2, k2. It means that we can encode k logical qubits into k plus 2 physical qubits with a distance of 2. That means that we have an overhead of 2 qubits. So we can take our quantum circuit, our QAOA circuit, add 2 more qubits, and we have some protection using this code. So you can see that the k qubits are on the surface. We call it the iceberg code because, I don't know, it has the structure of an iceberg. The k qubits are on the surface, and we have a top qubit and a bottom qubit. And the logical operators are defined in this way. Importantly, logical operators have weight 2. And we have 2 stabilizers, X on all qubits and C on all qubits, and that allows us to detect any single error. And our 2-qubit logical operators have weight 2. This is, again, very important because it will give us a very clean implementation on Quantinuum devices. Actually, every operator that has a physical weight 2 and this form, XX, YY, or ZZ, it's a logical operator of the code. So some of them are very strange, like this one here. If you implement an X on the top and an X on the bottom, this actually corresponds to this global operator, X on all logical qubits. I will show you that this opens new possibilities for designing, for implementing quantum circuits. So I was talking about the logical gates. What about the logical operators? What about the logical gates? The logical gates are Pauli rotations of this form and are implemented with physical rotation. So it's nice because for every logical gate, we only need one entangling gate, a Mollmann-Sorensen gate, this theta CZ gate that is native to the Quantinuum devices, that is a very clean operation. And then we have single qubit gates. In particular, I was talking about this global operator. So imagine that our quantum circuit requires implementation of a gate like this, a rotation over all qubits. This can be part of a quantum simulation experiment or some other more fancy QAOA. Using the iceberg code, this gate can be implemented using a single entangling gate, a single Mollmann-Sorensen gate between the top qubit and the bottom qubit. Without the iceberg code, what you need to do is a complete staircase of C0 gates, of entangling gates. So you can clearly see that the implementation of this gate with the iceberg code is extremely clean, and without the iceberg code has a lot of noise. All right. So one important point I want to raise is that in the iceberg code, the gates are not fault tolerant. This is the sacrifice we have to make in order to reduce the quantum overhead. All right? So if it's not fault tolerant, how can it work? Well, I'm going to give you a picture here where we have decomposed every possible error of a 2-qubit gate into 15 Pauli operators. And on the graph at the bottom, we are sharing the error budget for every Pauli operator on Quantinuum devices. So the iceberg code works because we can detect all these errors. The errors in green can be detected. That means that only these errors in red kill us. So effectively, we are reducing the error rate from the sum of all these columns to only the sum of these 3 columns. Actually, you can see clearly that we have been it has been happy coincidence that the errors that are not detectable, those in red, are very small. Okay, I was talking about the overhead that we need to add in the number of qubits. There was 2 extra qubits, top and bottom. And we have another overhead in terms of circuit preparation. This is what you need to run at the beginning of your quantum circuit. Then you need to run syndrome measurement circuits. This will be inserted throughout your quantum circuit. And then there is a final measurement circuit. So at any point, if any of the ancillary qubits, those in blue, is measured in the -1 state, you have to discard the circuit, forget about the result, and repeat the circuit. That's why it's an error detection code. It cannot correct the error, it can only detect it. And importantly, these circuits are fault tolerant. So there's a clever design behind them that makes them detect any single error that happens inside. Okay, let's move to the results. Quantum volume, we made a quantum volume experiment using the iceberg code. So this is a logical quantum volume, and I think it's the very first implementation of a logical quantum volume. The quantum volume experiment is extremely challenging because the circuit contains many gates. So this is for 8 qubits. So you need to have 8 logical qubits and 8 columns of random pairings of gates. And for every pair of gates, you need to implement a global 2-qubit gate that looks like this. So every block, every yellow block is composed of all these gates. So you can really see that this is a very challenging circuit composed of many gates. It's what I want to convince you that this is what I call an expressive circuit, in contrast to those that can be implemented with full fault-tolerant error correction nowadays. So what we need to do is that we initialize our quantum circuit, our iceberg code with this blue block. And then we take the quantum volume circuit and split it in different number of parts and insert syndrome circuits in the middle. And we finished the experiment with a measurement circuit. If at any point the blue ancillas is measured in -1, we discard the circuit and repeat. These are the results. Every point is an experiment on H1, I think H1, 2, and with a different number of syndrome measurement circuits. And as you can see, the green one passed the quantum volume test. That means that we achieved the necessary results on a statistical measure. The results are shown below. So I want to highlight 2 things about this. First is that this is an example where adding overhead, adding more gates actually helps. It's improving the quality of the results. You can see that these points are going up as we add more syndrome measurement circuits. And the other thing I want to highlight is that it comes at the cost of a higher discard rate. So if you want to improve the quality of your results, you need to pay the price of a higher discard rate. In this case, it's in the horizontal axis. You can see that the green one is maybe at 87, 88% of discard rate. All right, so there's another really impressive experiment using the iceberg code on a real quantum algorithm that uses phase estimation to estimate the ground state of a hydrogen molecule. So this is a toy experiment, a demonstration, but it highlights how the iceberg code can be used on a real quantum algorithm. In this case, the authors are also from Quantinuum. They wanted to protect this circuit from the errors. In these circuits, we have 1 logical qubit on the top row and 2 logical qubits on the bottom row. And we need to implement this control unitary several times, in particular k times. So this is a very expressive circuit because this unitary is a bit difficult. And then we have this seed rotation at the end. So how they did it, they took the circuit and decomposed it as I was showing before for the quantum volume with a few improvements. Well, first, the circuit is initialized, as I was showing before. And then this control unitary is decomposed into several blocks that are identical to each other, and they are repeated several times. Each block, you can see between the brackets, is composed by a logical control unitary gate, followed by the application of one of the X stabilizer, and then the application of another control unitary and the syndrome measurement. The novelty here was really well, there were a few, you can read them in the paper, but I want to highlight that they inserted the X stabilizer operator in the middle as a way to do dynamical decoupling. So they added some error mitigation technique to protect even further the results. And what they got was really impressive, I think. You can see on the vertical axis, we have the logical error rate, and on the horizontal axis is essentially the depth of the circuit, how many repetitions of the control unitary gate we have. So you can see the black dots are without any protection, without any code, and you can see that the error rate increases, and with the iceberg code, the red dots, the error stays almost constant at a value of 0. So it's almost like a perfect implementation of a circuit that is really deep, like 100 repetitions of the control unitary. And this, as I was saying, it comes with a cost, the cost of discard rate. You need to discard a large fraction of your circuits. In this case, they had to discard from 25 maybe to 70% of the circuits. I think it's not such a big deal if you can get positive results. You can really protect your quantum circuits at the cost of maybe multiplying by 3 or by 8 the number of repetitions. This is something that quantum computers nowadays can do easily, repeat more times the quantum circuit, but they really struggle to have other ways to protect the quantum circuits. Okay, so I want to finalize with a summary and an outlook. This is the main messages that I would like to tell you here. First, fault-tolerant quantum error correction is really the way forward of quantum computers to reduce the noise level to the point where every quantum algorithm will be able to succeed. But this comes at the cost of a very large overhead in number of qubits and number of gates. This overhead is too much for existing quantum computers. So if you want to protect your quantum algorithms like QAOA or VQE or some quantum Fourier transform on the existing NICs devices, you cannot really use all the power of fault-tolerant techniques. So that's what we tried with this iceberg code, is to bridge this gap. We tried to add a minimal amount of protection using the techniques from quantum error correction that will be able to protect our circuits on NICs devices without adding a crazy amount of overhead. The key was to sacrifice some fault tolerance, in this case the fault tolerance of the logical operators. We replaced that fault tolerance by a clean implementation of the logical gates. So in this case, the logical gates are really well adapted to our devices. And the cost we have to pay is a discard rate. We need to repeat our circuits more times. And at the moment, this is the bottleneck of the iceberg code. So for the next steps, what we want to do is to combine the iceberg code with error mitigation, with a better compilation, or even with some hardware improvements. And the goal will be to reduce the post-selection overhead. And I wonder if I think it can be potentially useful for quantum supremacy experiments on these devices. The extra protection that you get from the iceberg code can be what makes the difference between a successful and a not successful quantum supremacy experiment. And also more for the future, we would like to understand if the iceberg code can be part somehow of the future of fault-tolerant quantum computation. Maybe helping on some primitive like magic state distillation. And that's all I wanted to say. Thank you very much for your attention.
Thank you.